This ideal gas limit also works for low temperature, zero temperature.
That's a good question. So one key element there is energy and also is when the temperature is that low, they may not be that extent.
Let's see. Yeah, also water will freeze probably if you're trying to dissolve
The
something.
water will also freeze.
I see.
Yeah, that's more important.
Right.
So one may consider some.
Yeah. Cool. Okay, sure.
Okay, let's start it.
Yep.
Okay.
Recording in progress.
Welcome, semester. It's a great pleasure to have Arkya Chatterjee who are IT, supervised by Professor Schwinger. I can he already did very impressive work with Professor Weyl. And he's been working on this direction and also expand. His, today he's telling us about his
Invitation. Thanks for the talk about some work that I did with and we put out this work is about realizing certain get in my title. But going to be so axial chiral, the related noun. A lattice in a where back in in the field of lattice. I mean these are standard. One question for particle physics, because the standard model of particle physics is a chiral gauge calculations on a lattice that reflect the real world, you would utilize chiral symmetries and then gauge them. And there's a related problem of, for instance, back in the 70s, people used this, came up with of doubling the number of fermion modes when you put them on a lattice model. And people try to also use other kinds of models. What you mean by a derivative when you put a field theory in lattice. There are also other ideas motivated by coupling to SPTs in one higher dimension. And there's many other proposals for trying to publish of such fermions in a lattice model. In a very simplified setting. Chiral fermion problem has gone into like dynamic, which has a chiral addresses the kinematic aspects of the question. Another motivation point of view, a lot of many some examples are for instance are like mentioned, they involve mixed symmetry in form symmetry. And yeah, so this kind of tells us that it's interesting to whenever a UV microscopic model has certain anomalies, and once you've identified such a structure in the symmetry, you can kind of various constraints on the infrared low energy fate of that model. Here is is it possible to realize an anomaly of continuous symmetries, a finite dimensional Hilbert space, like a spin chain or single fermions? And the reason to ask this question is typically when you look at context, most of the lattice realizations are of anomaly. So it's interesting to ask whether analogs of symmetry can be realized in a finite dimensional Hilbert space. And before I get into the meat of the talk, I want to kind of remember what the main says Dirac fermion field theory in 1+1 dimensions that go by the name vectors, various names are identified of this field theory. Anomalies. We'll say this is something we and on the continuum, there must be a way in which that it's matched in the UV or in the microscopic modulation along the way. And in the end, we'll find a novel kind of gapless constraint arising which will be reminiscent of the kind of constraints that anomalies give in the continuum field theory. Yeah, so let me stop here and see if there are any questions about the motivation or
I have a question.
Yeah.
Suppose now infinite dimensional Hilbert space.
Yeah, I mean, in the context of infinite dimensional Hilbert spaces, in the last I've actually realized this particular anomaly in those models. These are like rotor models, like infinite freedom per site. I'll point out references to those along the way. So the field is a center of a component Y. And this is the left components of the Dirac. And looking at Y names of the Dirac. Independent for each both the charge conditions, and the psi left gets multiplied by a phase acted on by the U1 left, and the charge conjugation of the left movers interchanges the psi L and psi L dagger, changes particle and antiparticle, essentially. The same goes for the U1 right. And there are associated Noether charges which are conserved. Whenever you have a symmetry, there's an associated conserved charge, and those are given by this QL and QR. From these left-moving and right-moving U1s, it's these charges, which are just linear combinations of the left mover and right mover. You can see that the vector charge or the vector charge both, whereas the axial opposite phases on the left movers and the right movers. In this sense, on the left and right movers. These actually, which you can see by plugging in data, the Z2 these two symmetries have a some if for kind of phenomenon that Schwinger identified in a different lab. And this be associated to an infinite which if you take your for background with gauge invariance. It's an invertible vector. Okay. So this anomaly is a anomaly in the sense that it's captured by a Feynman diagram, namely this. In this particular case, I've chosen to represent this as coupling the theory to and then checking computing the current correlation function. This picture is represented as this. You're computing the divergence of this axial current proportional to the field strength associated to this background field, which I've represented. This was most clearly stated in a paper that followed Schwinger's paper by Johnson. And alternatively, as Schwinger originally showed in the equal time commutator of the current densities associated to the time components. So this is this J mu. In J mu, you plug in a time slice, and you look at two different spatial points. Of the of these two quantities, and turns through, so you get some kind of a contact term. Next to there's some non-trivial. If you stare at this cannot be traced. Dimensional Hilbert has a vanishing trace. But C number is such a commutator in a finite dimensional space. Whenever you have some kind of lattice model, either you in how of this in the lattice, you have to use an infinite. Answer your earlier question, this is these are kind of the I realize the finite dimension. So even though we cannot basically dimension that in a and that's the we'll try to identify the way to lattice being periodic boundary case. That central idea of this model is to try to put the two components in odd sides of the lattice. And this Hamiltonian often goes by the name of the community. I should have added a citation here. This goes back to Banks, Kogut, and Susskind in the 70s. So I'll often refer to this Hamiltonian as staggered fermion. This Hamiltonian obviously has a number conservation symmetry, which acts like on the fermions, on the fermion creation and annihilation operators. For the symmetry, which I'm going to call QV, which is given by this is essentially the lattice analog of the vector symmetry, which rotates both in the but does the question U1 symmetry? And to get to the composition fermions or real fermions, and so why this is the way to go. First, we recall from our definition, which is QL minus QR. Is which minus QR. Sign operator that flows to this CR in the to do so, it's useful to call them A and B. First important role. CR, it acts on the A and B. As that's okay. So following this distance, usual addition. And now we recall that the C fermion it can be diagonalized by going to momentum space. here alpha is the momentum space momentum mode associated to A, and beta is the one associated to B. In Majorana, fermions have the property that alpha of minus k is the dagger of alpha k. Same with beta. So this is kind of just like a number operator for alpha. This is number operator for beta. Dispersion looks like this. It's just a sinusoidal dispersion. At k near 0, the low energy mode is near here. They correspond to the left and right moving Majorana fermions in the. So AL and BL are sitting around here. AR and BR. Now, if we look at how the translation, the chiral translation operator, say, if you look at how it acts on the momentum modes for this phase here, and near which are near k equals 0 and k equals value of the left movers, one near the right movers, which means that so TB acts like but not of BL. So that's the full lattice translation. It for the right mover, since it flips the sign of both A and so we've now concluded that you translate. It acts like the so we can define the lattice vector and I conjugate the you QA argued that these are when you and this and by but chart several nice properties for the eigenvalue. And one way to see that is that QV, we already know, we know that this QV is just a number operator, which of course has integer eigenvalues, just counting, the number of occupancy levels. And TB is a unitary transformation. So since a cannot change the spectrum of any operator, the spectrum of QA is identical to that of QV. In other words, identical to those of QV, and hence they're integer valued. In a locality preserving manner on the fermions. So if you look at if you conjugate a at j at site j by e to the I theta qa, this is the theta rotation. It mixes it only with the B fermion on neighboring. It also gets mixed up only with the A fermion on a neighboring. So it acts in a locality preserving manner. Some of the complex fermions, the CJ. Linear. It is also a sum of one for all j. They commute with each other. Of almost local term. Almost local symmetry. In fact, as we showed, since QV is fully on site, completely on site. We should tell you the free. There's a price to pay. And don't actually okay. So what is the full structure? In fact, if you take repeated commutators of QV and QA, you actually generate something known as the Onsager algebra. This is discovered by Onsager in his 1944 paper solving the 2D classicalizing model. He had a slightly different presentation of the charges, but for our purposes, we'll define Q sub n and G sub n, which are indexed by integers. You can observe by looking at this that Q0 is nothing but QV. And this full set of generators, there's 3L of them, L being the number of sites. This full injections. So the G's all commute with each other, but the Q and algebraic structure. An S equation, you see that Q0, Q1 is some non-trivial operator. It's not. And it turns out that for fixed order one, Q ends with odd n. Flow to the vector charge of that. So this permanent the U1 vector vector. Where they organize the
Go to PUA 2 quantum because A on V symmetry so if it
actually, yeah. That's it.
is there like a easy way to?
Yeah, I should have talked about this, pointing this out. It should, so it you can see it from this expression here. So set theta equals pi. These two terms are gone, and cosine theta minus 1. So both A and B are both A and B get their signs flipped. And if you look at this, this also does the same thing. So this is e to the, you're looking at e to the I pi times and this number is either +1 or -1. So e to the pi is just going to be e to the I pi, right? Okay, I'm kind of doing air math here, but non-parity associated to the vector charge simply, I think, yeah. So it acts like this, right? So you set theta equals pi here. It also gets a minus sign. A and B components will also get a minus sign because
so
of this.
what you are showing here is QB and QA with is a pi in the front. They act as the sound component.
That's right. That's right.
Okay.
Yeah. Okay. A potential so famous theorem in the field of Kran's work implicating field charge that way that is quantized. And the returns charge but this goes back to the work of it's a particular definition, then a. So in particular, because Q1 and a related fact is that the eigenvalues of Q are quantized. However, it commutes with the vector charge. Again, this is something you could work out from the Zagreb algebra. You see that if you set n equals 0 and m equals either 1, those two commutators lead to the same operator. Add those to Q1 and Q minus 1, the commutator of that sum with Q0 Q tilde A does commute with the lattice vector charge. In the end, what we find is that we can either satisfy one but both of these charges or commented earlier, all of the QNs with odd n, they all flow to the they're all they're all good axial charges. There's between how these two charges act as symmetries on the while QA, as I showed, acts in a locality preserving manner. Either the if you write either the I theta Q tilde A and you conjugate the local fermion superposition over fermions, which get a sum of an extensively large number of fermion modes. Okay.
Explain what does this axial charge?
Talk if that's okay.
Thanks.
And that, but at the end of the talk, if that's okay. Okay. Discussing how the anomaly emerges from this go to momentum space. Like so important. We should like this, which are as QV number. Both the near equals L over whether K and near acting on the psi dagger, both left and right, just gives you +1 times. Whereas the axial charge, it gives you a plus or minus sign, depending on whether you're whether it's left moving operator. And those correspond to k equals 0 and L over 2 as we discussed before. These plus are exactly how the axial charge in the continuum acts on the fermion. Okay, so then kind of like the QV and QA charges on the lattice. The field theory or continuum vector and axial charges. So we and the mixed anomaly of the continuum symmetries either the the bubble diagram or the Schwinger to the lattice vector and axial symmetries. On rather than have it kind of emerge in the IR. Questions the new definition of anomaly, which is inspired by a global symmetry S is allows non and sort of definition of anomalies that from invertible symmetry. Tested update that definition to this non-invertible, but it's identical. Inverse paper here, so I end between for this tree Gonzaga algebra, which remember associated charges, and set that number could not for those symmetries. And here that gapless. This result here tells us that the lattice symmetry also has an anomaly. So that's how we kind of realize the anomaly on the lattice. As I sort of alluded to along the way, both the vector and the axial symmetries, they're individual, and that's reflected in the fact that it's possible to open an energy gap with deformation either QV and break QA, or preserve QA and break QV. To have there's a constraint that prevents us from open observed. So the first step in to note that the Z4 subgroups of this U1V and the U1A as this kind of opposite translation operators for the B and the A fermions, respectively. Both of these U1 symmetries implies B times TA inverse symmetry. It any such coupling, any such local coupling between A and B Hamiltonian. Two. Okay. I think the next step is what kind of couplings that are only between the A's would break the vector symmetry. Finite order 1 number. But you could choose any n. As long as n is not. So this is these are allowed. You see such Hamiltonian is gapless. Does this answer your question, Yojan?
Incident in the case in some, say, polynomial. Is that?
Even allowing you to like
understanding is in
I want in the larger n to be
this Apollo.
but let me answer. This dk A and B. Other transformation. So in some sense, like coupling. Like combining the kind of rule.
Is it? Case symmetry.
So, oh, you mean you put the power out here, like
Yeah. So I have
complex.
I have some overall coefficient that's proportional like 1 over n squared. Is that symmetric?
That's a good. I mean, I haven't thought about this. Hamiltonians that were kind of like almost local in this sense. But this is a good. Yeah, I have thought about.
Yeah. Previously, previously with some other people, we proved a theorem for this kind of Hamiltonians.
I see, I see. Okay. Yeah, we should talk offline about that. Yeah. It's interesting.
Maybe related question. So suppose I just have a finite sized chain regarded as a quantum mechanics problem. Then is it possible to have a unique ground for this symmetric Hamiltonian?
Yeah, I think in that case, like depends on the boundary conditions. For the periodic case, I think there's a ground state degeneracy. Ground state. So when I say gapless here, what I really mean is I'm gaplessness as there being a finite order 1 gap between the ground state and the I think you're asking me a finite system.
I'm just asking to check at 0 plus 1D, or is it only and not in one? Since the QV and QA do not commute.
That's right. How I would define
degeneracy.
I see.
Case.
To maybe not what you're talking about. Condition there would be some zero modes which would
I see. Okay.
You would get a
proof as a space. It's just the Hilbert space. Like in general, when we say like K-chapter phase or even gap, we allow like adding
here means to deform and so this
that's still it can okay. I see.
terms that
Yeah.
That's we're kind of any ground.
Symmetry, symmetry.
Yeah.
No,
Oh,
is it? So
so you can
naively, I would
define it
take
for sure. Right.
Yes.
You can define it for sure, but I think the problem is that L and a QR would not have integer quantized eigenvalues. Right. So it has the same problems as this that I mentioned earlier. So in other words, they wouldn't act locally for a finite lattice. But in some thermodynamic limit, they might approach. They'll still approach QR.
Sorry, what's the relation between acting locally and have integer eigenvalues?
Yeah, maybe those are not related, but those are both true. L and QR. Yeah, sorry. Maybe they're not related.
I see. There is still a chiral version of the Schwinger anomaly, named like left Q, a J left commutator is some
That's
delta
right.
function.
That
is the lattice manifestation of that. But you say that's
right.
Defining is more challenging because this naive way does not give you.
I think in other words, I want to say that Q, even if you define this Q left, is just e raised to I 2 pi times Q left will not be 1. So it won't be a faithful one. Does that make sense? Because that's not a compact symmetry. It's symmetry.
I see. Okay.
System size going to infinity limit, you will end up getting the continuum.
So just to extend this discussion of only one of the argument based on the entanglement structure that the space is a tensor product, then not even mention this is not allowed. Meaning just having it is based on some assumptions of the entanglement structure.
I mean, in this case, I don't think there's, you don't have right mover.
I was talking about what Yunqing was asking about. Yunqing was asking about the case have Weyl.
Oh. I see.
The theory is still non-chiral, but mask theory, like whether I can realize you or fermion, for example.
Okay.
Question.
Okay. Still being anomaly free. More general definition of allowing symmetry, but in the paper, I'm not gonna go to model for one T lattice model. that we just conclude how massless you want, and we leave them closely parallel, which rules my formation. Yeah, there are a few. So you're thinking using non is this u1 times u1, even in 1 plus 1d, and they're signaled by various kinds of commutational relations, morally similar to the Schwinger term. It'll be interesting to see if it can also be realized in the lattice. And let me quickly Bosonized version of the problem that was raised in the question. So this is some work that's still in progress. If we bosonize the Hamiltonian, you get this get the XX model. This I shouldn't be here. This I shouldn't be here. You get the XX model, or as some people call it in the literature, and the IR limit of this Hamiltonian is, and the compact boson CFT has so those are the symmetries that these vector and axial charges will get mapped to under bosonization. And I like so sorry, this should have been W. Bad. This is the winding symmetry. Symmetry is this spin rotation symmetry, whereas the axial symmetry gets mapped to this kind of scourge. And these two are exact symmetries of the XX model. And indeed, symmetry go by the name of momentum and winding. And we also realized a quality since R to 1 over R exactly on the lattice. And tuned if you want to know more about this. With that, I want to end my talk. Thank you for
the very interesting talk. Any other questions?
Graph degeneracy depend on the boundary condition, but raising the anti-periodic boundary condition.
That's a good the slides. It had this kind of, I wrote this AJ, BJ plus 1 and summed it from J equals 1 to L. But I did this one. You actually get a symmetry of this. Both
examples of with both symmetry.
Yeah, that's a reason. Be the case. It's requiring both U1 V inverse, but you see that TB and TA TB is just acting like T. In other words, UN. So yeah, that's kind of general to lattice. This if you just kind of
Question. In the last value. Is an anomaly. But that's
only generated. Right. So question is one not the same as the continuum symmetry. So in usual matching, the symmetries in the continuum and the they match at least on some subgroup, and so then you can like kind of match the index associated to those subgroups. But here, because the U1, like the two U1s, they don't commute on this. Yeah, I'm not sure whether one can. I mean, certainly you cannot define the index. You just treat the U1 vector and U1 axial as like independent U1s, coupling gauge fields, and so on. You cannot do independent symmetry.
Yeah.
So yeah, you'd have to do something more clever to define it. I'm not this point.
Thanks.
Oh, some technical things. So it's even, right? L is even.
That's right.
Yeah. So what are remain the same, and what will change? For example, just answer ago.
Yeah. So
low, yeah.
So, let me think. So one naive thing is that the boundary conditions for the left movers and right movers will be different. With an even number of sites, both of them have the same conditions. Like sites is like inserting a defect in the fermion theory.
You have the chiral fermion parity defect.
Right. The fact that I argued earlier that translation, like the full translation, TA times chiral. So yeah, that kind of tells you that if you add another right? What happens to this like unzagor algebra structure? Yeah, do anything smart to say about that?
And will change, right? So can be
That's right.
modified. The charge, so and then the unzagor algebra is also
This the bosonized story. Where the of the moment it's with what you're asking for. You're
conclude this seminar. So then